Welcome everyone and thank you for joining. I'm Roberto De Vecchi, as already said, and today I will present you how real-time models are transforming the digital engineering. The focus is VI-CarRealTime, our vehicle simulation environment, which supports engineers throughout the entire process, from concept phase through development and integration, all the way to virtual sign-off. Over the next approximately 40 minutes, I will explain the main challenges the industry is facing, introduce the unique strength of VI-CarRealTime, and show real customer case studies that prove its impact. This will give you a complete picture of how real-time simulation is used in practice today. Let us begin with the challenges of modern vehicle development. First, development cycles are becoming shorter. Companies must bring a new vehicle to the market faster, so time to market is one of the key, most critical KPIs. Second, fewer prototypes are being built. This reduces cost, but also limits opportunities for physical testing, which increases reliance on accurate simulation. Third, the systems inside modern vehicles are more complex. Electrified drivetrains, ADAS, active chassis system, and sophisticated electronic controls all need to be integrated and banded together. Finally, development is global. OEMs, suppliers, and partners are spread across multiple locations. This requires collaboration platforms that allows models and results to be shared reliably and securely. These are the realities that shape our approach to simulation. What is VI-CarRealTime, and what we need to do today to meet the challenges just mentioned? We need accuracy, so that engineers can trust the simulation results. We need efficiency, so that results are available quickly enough to guide decision-making. We need the ability to evaluate design rapidly and optimize them early without waiting for prototypes. We need seamless collaboration between global teams and suppliers. And finally, we need one consistent model that can follow the entire process, from the first design concept to the final validation. This is exactly what CarRealTime has been designed to deliver. Robustness, accuracy, and efficiency are not optional in simulation, they are essential. This is why they are first unique strength of VI-CarRealTime. The tool is tested daily by OEMs and suppliers worldwide under some of the toughest development conditions. With it, engineers can evaluate tire performance virtually before a prototype exists, develop next-generation chassis control features, deploy advanced drive-by-wire systems, and even prepare a vehicle aimed at record-breaking performance. What matters most here is that engineers do not waste time waiting for results. The solver delivers feedback instantly, so focus stays on development decision rather than on managing the tool. That is why leading companies choose VI-CarRealTime, because it's fast, accurate, and reliable, enough for their most demanding programs. Accuracy also depends on starting from validated models. Starting data are really important. With VI-CarRealTime, engineers can benchmark their design against internal and external targets with confidence. Through access to the ADAS library of validated vehicle models, they can compare against trusted references from top brands. The KNC wizard makes it easy to build a benchmarking model quickly using real suspension data or experimental KNC maps. On top of that, visualization tools like the Animator allow engineers to make direct visual comparison across analysis or against CSV data. It's as well possible to transfer data to external post-processing environments. The result is a workflow where benchmarking is fast, intuitive, and directly tied to real-world vehicles, ensuring the model delivers robust and accurate insight. Robustness also means being flexible enough to integrate complex mechatronic systems. VI-CarRealTime supports this through customizable connection for control logic. Engineers can deactivate subsystems to create custom setup or insert their own user-defined logic at different points in the model to control specific vehicle function. Equally important is seamless integration of external models. Subsystems developed elsewhere can be connected from matter of Simulink, FMI-compatible tool, or directly through C and C++ code with extensive solver API set. This capability ensures that no matter where a subsystem is developed, it can be brought into one consistent environment, preserving both accuracy and efficiency across the full vehicle model. Efficiency is not just about how fast the solver runs. It's also about how engineers interact with the model. Complex models with thousands of parameters can be difficult to manage if not organized correctly. With VI-CarRealTime, this is simplified through the override file system. Engineers can manage different model variations without duplicating data. They can focus only on tunable parameters relevant to the task at hand, while the rest of the model remains protected and unchanged. This system also makes it possible to limit edit when models are shared with suppliers, safeguarding intellectual properties, but still allowing necessary adjustments. The result is that engineers can run analysis more efficiently, spend less time on model housekeeping, and more time interpreting results. That is what keeps a simulation scalable and usable even in the most demanding projects. Let me illustrate robustness, accuracy, and efficiency with a concrete customer case, Goodyear, to start. Goodyear needed to improve the way they developed and validated tires. The biggest challenge was correlation. Simulator results had to match road tests with high precision. Without this, simulation could not replace expensive prototypes. The process itself was costly and slow because it relied heavily on physical tire builds and on road testing. Validation was complex, covering many platforms and specifications, and driver feedback could be inconsistent without robust model. In short, the combination of high cost, long lead times, and inconsistent data was holding back tire development. To solve this, Goodyear established an integrated workflow with VI-CarRealTime as the core dynamics model. Finite element data was reduced into real-time compatible model, leveraging a built-in CVTime interface and then used in driving simulator assessment. Results were validated with correlation metrics against the road test. Crucially, they created a continuous loop, model to simulator to road and back again. Each cycle refined the model, improved fidelity, and built confidence that virtual testing was a reliable part of the development process. This approach delivered clear benefits. Goodyear achieved strong correlation in demanding conditions like high speed handling. They were able to evaluate tire performance early in virtual environments before prototype existed. Physical testing was reduced, which saved cost and accelerated design iteration. Finally, the process was scalable, enabling collaboration between Goodyear's global teams in Akron and Luxembourg. Together, these results showed that VI-CarRealTime could provide the robustness, accuracy, and efficiency needed to transform tire development. Virtual tire development is nowadays an established methodology implemented by many tire makers and OEMs. Let's now have a look at the rapid design evaluation, so the second key topics we started from. Rapid design evaluation begins with flexibility. In VI-CarRealTime, engineers can reuse subsystems from past projects by accessing them through database-driven storage, saving time when starting a new program. They can also disable non-critical details to focus only on what really matters for a particular study. Baseline setups can be adjusted with simple cadence scaling factor, providing a fast way to adapt an existing model. On top of these, ready-to-run models come with built-in control and lookup components, so teams can quickly move from setup to testing, and when entirely new designs are needed, engineers can create suspension concepts directly via VI-CarRealTime, using the template-based suspension model without needing a separate design tool. This combination of reuse, adjustment, and creation it is possible to go from an idea to a testable suspension in a very, very short time. Once a model is ready, the next step is testing it. VI-CarRealTime includes a rich test mode library that allows engineers to run standard evaluation instantly. They can conduct both open loop and closed loop tests. Using VI driver, execute complex maneuvers like ISO double lane change and build custom events with VI event builder to match the specific workflow. Advanced tire models such as various magic formula from Paseka, F-tire, CD-tire, Swift, Ride Seat, and many others can be used to increase fidelity. And with the error of the VI grid mesh, engineers can access extensive proving ground roads library and create high-fidelity road surfaces. This ensures that rapid design evaluation is not just fast, but also realistic, covering the same condition vehicles will face in real world. Rapid design evaluation is only useful if performance can be measured consistently. VI-CarRealTime provides exactly this with fast and reliable KPI assessment at every stage. Reference events can be defined and promoted to standard test cases so that all engineers use the same benchmarks. Performance metrics and acceptance criteria can be clearly set, ensuring the results are comparable across teams and projects. Finally, one-click execution with automatic report generation makes it easy to run an assessment and immediately share the outcome. This means KPIs are not just fast to obtain, but also standardized and transparent, which is critical for confident decision-making. A highlight of rapid design evaluation is the max performance event. With just one click, engineers can assess vehicle performance around the track. Internally, this specialized event executes a two-stage evaluation process. The initial phase performs a rapid performance estimation using a quasi-static approximation of the vehicle model, enabling fast iteration. This is followed by a verification phase that utilizes the full dynamic simulation model, incorporating control system and any additional model extension. Through an iterative refinement, the VI-CarRealTime solver computes the maximum achievable performance along the given driver trajectory. The framework also supports the customization of the validation criteria, allowing for tailored evaluation across diverse application scenarios. This feature provides immediate data-driven insight into how design changes affect the overall performance beyond the pure lap time. That is, of course, the starting target, but is not enough to judge when things are really set up at best. Single Vehicle, a Californian-based hypercar manufacturer, is developing some of the most advanced performance cars in the world. To meet their ambitious target, the team needs to evaluate innovative suspension and layout concept quickly, balance extreme performance goals with limited developmental resources, make confident data-driven decisions early without relying solely on prototypes. To address these needs, Singer has recently adopted VI-CarRealTime. Their intention is to use the software as a backbone of a new virtual design exploration workflow, enabling them to run rapid KPI assessment, such as the lap time simulation we have just seen, or any other performance envelope simulation, integrate custom control logic into the model for realistic evaluation, explore multiple design alternatives virtually, and iterate with much greater speed. By bridging VI-CarRealTime into their own tool, Singer aims to accelerate innovation, so shorten the time needed to develop and validate design choices, increase agility, switch between alternative concepts without the cost of building physical prototype, and build confidence early. Use simulation data to confirm hypercar level performance targets before any prototypes is produced and brought to track. Now let's let's move a little bit ahead and let's talk about optimization and design exploration feature built into the VI-CarRealTime. With VI-CarRealTime, any dataset or event can be turned into a ready-to-use workspace. Engineers are not limited to one-off simulation, but can set up structured study that reveal how different parameters influence performance. Parameters defined in subsystem generated from matrix simulating or from FNUs can be promoted as study factors. So optimization includes not only the vehicle dynamics model, but also the connected control logic. Responses can be defined either from the VI-CarRealTime output or from custom function, giving full flexibility. The platform supports multi-objective optimization and design of experiment, so engineers can explore trade-offs and find a robust solution instead of relying on trial and error. Let us look at how this concept is applied in practice with the case of Astemo. Astemo, a global Tier 1 supplier, was working on damper development for battery electric vehicles. This task is especially demanding because battery electric vehicles have unique constraints. Heavy battery packs affect weight distribution, comfort expectations are high, and efficiency targets are critical. The challenge was to design and tune damper quickly while balancing all these competing requirements. Traditional approaches based on multiple prototypes and extensive test campaigns were simply too slow and too costly to keep the pace with the needs of the BEV market. Astemo addressed this by adopting VI-CarRealTime for virtual damper evaluation. The first step has been to hook VI-CarRealTime their own specific damper model and controllers. Then, leveraging optimization and design exploration tool, they were able to create structured workflow that used design of experiment and AI-enhanced tuning methods. Instead of relying only on physical iteration, engineers could vary parameters virtually and see the impact on comfort, handling, and efficiency. The integration of optimization allowed them to move beyond validating one design at a time and instead explore the entire design space systematically to identify the most promising solutions. This new process delivered measurable benefits. Astemo was able to accelerate the suspension design cycle, responding to RFQs faster and with greater confidence. They reduced reliance on physical prototypes during the early development phase, which saved both cost and time. They also improved the alignment between virtual prediction and real-world performance, thanks to AI-enhanced tuning. Most importantly, they could deliver optimized solutions that met VAD-specific requirements for comfort and efficiency. This case shows how optimization of complex systems built around VI-CarRealTime really helped suppliers stay competitive in a fast-changing industry. And on top of this, the confidence generated by this initial step convinced Astemo to further expand their methodology into driver-in-the-loop and hardware-in-the-loop. This feature is all about seamless collaboration. Modern vehicle development is never done in isolation. It involves OEMs, suppliers, and global teams. For collaboration to work, all parties need a way to exchange data reliably without wasting time on reformatting or building models. With VI-CarRealTime, vehicle data can be integrated from many different sources. Suspension KNC maps can be imported directly from ANSCAR or other simulation tools. Experimental KNC data can be loaded through the KNC wizard. Generic vehicle data can be added with build mode or the MATLAB model API. On top of this, the model definition is almost entirely based on standardized text files like XML, JSON, and so on. This makes data bridging extremely easy. The result is a workflow where everyone contributes their data into a single consistent vehicle model. That makes collaboration much smoother because engineers can focus on solving problems together rather than fighting with incompatible tools. Collaboration also means that the vehicle model must be usable in many different environments. With VI-CarRealTime, models can be exported as FNU packages for applying simulation in any FMI-compatible tool, or deployed on HIL platform such as DSpace, National Instruments, SpeedGoat. They can be run as self-contained FNUs without needing extra software installation. Data can also be exported in encrypted form to protect intellectual property when sharing with supplier. The model is fully compliant with the FMI standard for co-simulation and is scaled seamlessly to HIL, software-defined vehicle workflow, and even cloud environments. But what happens if instead you have an FMU component and you want to use it? No problem, VI-CarRealTime can act as FMU master and orchestrate multiple FMU instances on your behalf. This flexibility ensures that a single VI-CarRealTime model can travel across the toolchain, across different companies, and still deliver consistent, trusted results. A key enabler of collaboration is direct integration with MATLAB Simulink. MATLAB Simulink is still, I would say, a big player in all vehicle development. Everywhere you have a controller, most likely you have a MATLAB Simulink environment. With VI-CarRealTime, engineer can exchange data bidirectionally with Simulink, connecting vehicle dynamics directly to control logic. This means that control engineers and vehicle dynamics engineer can work in the same loop with no translation effort or duplication. Subsystems developed in Simulink can be added as auxiliary components in the vehicle model, while vehicle dynamics data from CarRealTime can flow back into the control environment. This kind of seamless interface reduces silos inside an organization and helps engineers work as one integrated team. Another important element of seamless collaboration is intellectual property protection. When OEMs and suppliers exchange models, it is vital that sensitive know-how is safeguarded. With VI-CarRealTime, models can be exported as obfuscated packages. This means the model can be executed by partner, but internal details remains hidden. For example, OEMs can distribute some file to run on external driving simulator or embed supplier simulation models into the workflow without exposing sensitive data. The same applies to deploying FNUs on both SIL and HIL platform. The model runs securely while the intellectual property is fully protected. At the same time, editable parameters can still be maintained via override file system. This gives partner enough flexibility to run their tests and make adjustments without even revealing the underlying confidential logic. This balance between collaboration and protection is what makes VI-CarRealTime practical for real-world industry workflow, where multiple parties need to work together without compromising IP. Brembo, a global leader in braking system, is an excellent example of how VI-CarRealTime enables seamless collaboration. At their coding hub in Sunnyvale, California, Brembo integrated VI-CarRealTime into their software development process. The objective was clear: to validate new braking control logics virtually before they reached the vehicle. The adoption of VI-CarRealTime, together with the MATLAB Simulink interface, lies the foundation for workflow that are more efficient, agile, and collaborative. Instead of waiting for physical tests, teams can share results earlier, test more scenarios, and refine their software faster. Specifically, Brembo used VI-CarRealTime to support the virtual development and testing of braking control software function. This means engineers could validate control logic before ever putting them in a real vehicle. The integration with MATLAB Simulink was key. Brembo's control algorithms were seamlessly connected with the VI-CarRealTime vehicle model, making the workflow smooth and consistent. They also made use of a unified, high-fidelity real-time simulation environment. This minimized configuration time, so new vehicle dynamics simulation could be set up quickly and reused across different projects. The benefits of this approach were tangible. First, development loops were shortened. Virtual validation reduced dependency on physical testing, speeding up software development cycles significantly. Second, seamless integration between the Simulink interface and the VI-CarRealTime model ensure an efficient collaboration between Brembo's controls engineer and vehicle dynamics specialist. And third, faster time to test was achieved. Engineers could evaluate new braking logic more quickly in both hardware-in-the-loop and driver-in-the-loop environment. Together, these results demonstrate how VI-CarRealTime enabled faster, smarter, and more collaborative control software development at Brembo. Let's now explore the importance of having one consistent tool for the entire development process. With VI-CarRealTime, you do not need separate model for each stage of the workflow. The same universal vehicle dynamics model can be used across desk simulation, high-performance computed encounter campaign, software-in-the-loop setups, hardware-in-the-loop rig, driving simulator, and even vehicle-in-the-loop testing. Think about how much time can be saved just by this. One model that can go across the entire spectrum of development needs. This consistency is critical. It means that the results from one stage can flow directly into the next without translation error or rework. Engineers across different disciplines and locations all use the same backbone model, ensuring that validation is both efficient and trustworthy from the first concept to the final sign-off. This is a super powerful capability. VI-CarRealTime also serves as a unified tool for performance development, supporting both objective and subjective evaluation. On the offline side, engineers can group multiple analyses with test mode fingerprints, apply design of experiment and multi-objective optimization, and visualize results with customizable plot, as we said with the animator, for example. Reporting can be automated with Python scripting, and results can be imported directly into MATLAB or other ASM MDF compatible tools. On the online side, the model can be deployed on any VI-grade driving simulator from compact rigs to full motion system. Setup management is simplified with the override file, making it easy to test multiple configurations quickly. The model's scalability means engineers can start with simple configuration for early concept and then increase the complexity for final validation. This gives both objective number and subjective driver impression, all from the same trusted vehicle model. Mercedes-AMG faced mounting pressure to accelerate their developing cycle, while at the same time managing an explosion in system complexity. They were working on integrating a rectifier powertrain, active chassis system, and advanced controller. Each of these subsystems is demanding on their own, but the real challenge comes when all of them need to work together in one coherent vehicle. Traditional processes limit cross-functional insight. Vehicle dynamics team, control engineer, and hardware developer often worked in silos, which delayed model validation and slowed down decision-making. IMG needed a way to connect this domain and bring consistency into their workflow. To address this, IMG implemented a multi-layered simulation toolchain with the VI-CarRealTime at the core. The model became the common language between tools such as AdvanceCar, Simulink, TargetLink, CAMSIM, FMU, a bunch of FMUs coming from everywhere. By anchoring everything around the VI-CarRealTime model, IMG could connect vehicle dynamics, control, and hardware representation into one consistent loop. This meant they were able to use the same validated model across software-in-the-loop, hardware-in-the-loop, and driver-in-the-loop stages. The toolchain became multi-layered, but also unified with VI-CarRealTime, acting as the backbone. Here we see how Mercedes-AMG structured their solution. They built a multi-layered simulation toolchain with the VI-CarRealTime at its core. This toolchain supported the rapid development and the integration of both hardware and software systems. What made this approach effective was cross-functional collaboration. By using the VI-CarRealTime as the dynamic simulation environment, IMG enabled seamless communication between teams working on vehicle dynamics, powertrain, and control software. Everyone was connected to a unified digital backbone. This setup provided a platform that both was stable and agile, allowing system fusion and joint model validation across different disciplines. It meant that engineers in separate departments could work on the same model, validate their subsystem together, and move forward without the delays that come from isolated workflow. The toolchain spanned from SEAL, so software in the loop, to driving simulator, to drivetrain test benches, all tied together by one consistent vehicle model. This ensured that validation could take place early, often in realistic conditions, supporting IMG goals of achieving early virtual sign-off. The results were significant for IMG. They achieved early virtual sign-off of critical control functions with reduced process waste and cut physical test dependencies. Driver-in-the-loop simulation provided more realistic evaluation, improving the alignment between subjective driver feel and the objective data. Function testing, fault handling, and regression checks could now be automated across integration stages, which made motion control calibration more robust. And the consistent VI-CarRealTime based development loop ensured smoother hands-off between simulation stages, reducing time to sign off and boosting cross-department efficiency. In short, IMG proved that one consistent model can cover the complete development cycle, from concept to the final sign-off. So, as we close, let us recap the 5 key strengths of VI-CarRealTime that we have seen proven in customer application. First, robustness, accuracy, and efficiency. VI-CarRealTime has been validated in daily use under extreme driving conditions, delivering results engineers can trust. Second, rapid design evaluation. The tool enables fast iteration cycles, giving instant insight and reducing dependence on costly prototypes. Third, built-in optimization and design exploration. With integrated DOE and optimization, engineers can find the best solution and explore alternatives systematically. Fourth, seamless collaboration. Models and results can be shared effortlessly across teams, platforms, and global sites, with full IP protection where needed. And finally, one tool covering the complete development process. From concept to virtual sign-off, the same unified model supports every stage of development. This is why leading companies rely on VI-CarRealTime. It allows them to move faster and to make smarter decisions and collaborate more effectively. With this, I would invite everybody to have a look at our website using the QR code that you see on screen, where you can get even more information related to VI-CarRealTime, and get in touch with us for a demonstration or even more or answer any of your questions. Thank you, everyone.